Hello, welcome to the Build Lab. In today's video, we will build from scratch one of the most powerful tools in matching patterns. It's the regular expression engine. In short, we call it Regex. Here is a preview of what we're gonna build in this video. Let's import our package that implements our engine from core Regex. Import our class called Regex. After that, we called the method called match. It accepts parameter Regex. Let's say, for example, we give it A or B, and we give the literal, simply for testing, C. If we do a simple check, if the two is matching, the two arguments are matching, we simply print matching. Otherwise, we simply print not matching. So let's run the script and we're gonna see it says it will return false and it prints not matching. So as you see, it's not matching. If we give another example, let's say for example A, it will say matching. This is a complete project. I put it in my GitHub. You can go and check it. I will put the link in the description. As you see, our Regex, it calls Chameleon. It has all building parts, the architecture overview and other things. And also in this Regex we implement 4 operators. It's the OR and the clean star, grouping and escaping. So go and check this repo and have fun. Now so before jumping into the code, we should first of all establish our system architecture. So what we expect in this video, we implement this architecture. It accepts a Regex as an input and the letter as an output, and finally it gives us either true or false. So inside our big model there is 2 submodels. The first model is called generator. This generator is accept as an example Regex like A or B, A star B and other ones, and then it generates a state machine and then it forward it to the acceptor, and the acceptor it take it and read the literal text and then it generate a boolean, either true or false. Let's take example for the state machine. This is a state machine. 0, it's called the initial state, and 1 is the final state. And the other ones, A and B, it calls transitions. So let's for example read the text AAA, and dollar it simply represent the end of the string. So our cursor it read the first A, it consumes the first A, and we are in the first state. So I read A, I consume A, so I make a transition with A, and I'm in 1. So the cursor will increment by 1, and I'm reading A, but I'm in the final state. So from here, I have no other transition to go on. So this is not matching our Regex. Let's take the other example. Our cursor starts from here, it read A's, and we are on this 0 state. So I read A, so I make a transition to the 1, to the state 1. So I increment the cursor, so I'm at the end of the string, and my cursor on the state machine is on the end of the state machine. So we conclude that this A it's matching with the regex. So for now, let's jump to the code and implement hard code this state machine just for simplicity. And furthermore, we would make the model generator that simply it takes whatever the regex and generate whatever state machine. So let's move on. So let's start by creating our first class. It's called automaton. It will encapsulate all necessary attributes, and by building our project we will add more and more methods. So for the constructor, it will accept alphabet, we initialize it by none, and initial states of our automaton also initialize it by none, final state also initializes by none, and all states of our automaton also initializes by none, and finally our set of transitions. So let's initialize all attributes of the class. Self.alphabet call alphabet self.initial state self.final state also self. All states of our automaton, and finally the set of transition. So now let's add one more method just for debugging purposes. So it will return a formatted string alphabet self alphabet, then initial state self.initial state, also as final states self.final state, also as all states of our automaton self.states, and finally the set of transitions. Self.transition. Now let's test out this automaton class. We simply say automaton. We will make the example of regex A or B. So for the alphabet it accepts A and B. For the initial state it's 0, for the final state it's 1, and for all other states it's 0, 1. For all the transition of our automaton from 0 state, and we consuming the character A, we go to the transition 1 to the final state, and also from 0 and we consuming the character B, we go to the final state 1. Let's print this out. Print automaton. Let's run our script. Okay, it says it's should be a character. Okay, let's rerun. So as you see, this is the definition of the automaton A or B. Automaton accepts alphabet, init state, final state, and all other transitions. So now let's continue, and we will create another class for Regex, our Regex engine. So in this class we have three methods. The first one is a static method called generator. It accepts a regex as a parameter and it returns an automata. So for now let's pass it and go to the other method. The second method is also a static method called acceptor. It accepts an automata or a state machine and a literal. So let's pass it for now and define another static method called match. It accepts a regex and a literal. So inside this match method we should have an automata returned by the function generator. We pass a regex. It simply return a state machine, and from here we return simply what acceptor return regex acceptor. We pass automaton generated by generator and we pass the literal, so it returns a boolean. So for now let's define the generator. We simply hard code our automaton. We simply code this automaton inside the generator function and we return the automaton. And in the acceptor method we will initialize a state. This state is the entry of our automaton. It's the initial state, automaton dot initial state. So we copy that and we pop the value. Why we do this copy? Because to avoid that initial state will change the original automata because we do a pop. So let's import this package from copy import copy. So we are ready to go. So from here we loop over each character in the literal. So if the character not in the definition of alphabet of our automaton, we simply return false. This is in case we don't recognize the character consumed, the consumed character. Otherwise we test if the state that we are in and with the consume character, if it is not in the automaton that transitions, that means we have no transition to go. It simply means we returns false. So from now we will change our state to the new state automaton.transition, and we make our transition by state by consuming C, and we copy that and we pop the value. So after the loop it finishes, we simply make a final state to check if we are in the final state or not. So we do state in automaton.final state. So let's check that by executing our program and doing a simple test. Let's remove that. If Regex dot match, we give it our example, it's A or B. Keep in mind that generator we hard code the automaton, so for now the regex will do nothing, and we pass our test. Let's say A. If it's match, we do a simple print matching, otherwise we say not matching. Let's test that. So it's a matching. So if you would decide to do something else like K, it will print not matching. So keep in mind that we hard code this just to prove the concept. By making progress and improving the project, we will make an algorithm to generate an automaton, whatever the input is, whatever the regex is. So let's make another example for regex equal an A star. So I will show you a automaton for this example. So as you see here, we have one state that represent this automaton represents a regex A star. This star is clean star. So this automaton will recognize a words like epsilon for empty string, and A and double A, triple A, and so on. So we have one state. This state is initial state because of this arrow, and also it is a final state because this arrow. So we have here a transition, a loop transition by A, and we get on and on and on this state. So let's hard code this example in our generation mode. So we go here and we copy comment, we do a command for that. And we will do a return for the new automaton that represent A star. So for alphabet, we only have A. For the initial state, we only have one initial state and one final state 0. All the states are 0. And for the transition, we have one transition. From state 0, we consume A, we get into 0. So let's return that. And let's test that. So let's comment that and make another test for I star. Let's do an empty string. So it will says matching. Okay, it says matching. So let's do AA and execute the program. It will say matching. Let's do AA. So it says also matching. So this is the idea of how we will build a regex engine. So from now we will just modify our generator, because our acceptor and match, it's all a method that is generic. It stays and waiting for a generator to generate the automaton. So as you see here, we are developing all the thing in one file called main.py. So let's make some enhancements and make our project more modular and efficient by doing some packaging. Let's create a package called the core package, and inside it we will create a file called Regex engine. Also, as we will create another file called automaton, and we will do some copy paste. Let's copy our automaton class in the file automaton. Also, as let's copy the Regex class in the Regex engine file and import the copy So let's delete all that and retest our projects. So from core dot regex engine import regex class. Let's do some simple tests. Regex dot match. We are on the test a star, and let's do some a. And if it's true, we will print matching. Otherwise, we'll print not matching. Okay, it says automaton is not defined in the regex engine. So let's go to the regex engine and do some import from core dot automaton import automaton class. Let's do simple test. So here we are, the code is running correctly. So as you see, our main file, it's more cleaner. So now let's improve our generator model and let's jump to the architecture part. So as you see here, you remember this architecture. We have the regex as an input to the generator model will generate a state machine, and the acceptor will accept a state machine and the literal, then it generates a boolean, either true or false. So here I introduce a more details architecture. I did not change the original one, but I add more submodels to the generator model. So let's see here. We have three main parts on the generator model: a lexer and the parser and the automaton builder. So the lexer will take as an input a regex and then generate tokens, a list of tokens. And there the parser will check if the tokens are syntactically correct and they follow our grammar rule, and then the parser will generate an abstract tree, or in short AST, and this will forward it to the automaton builder, and this automaton builder will help us to generate the final state machine. So let's take an example here. We have two regex. The first one is syntactically correct because we have A or B or C, but the other one is not syntactically correct because we have at the end or. So let's take the correct example, A or B or C. The lexer will generate tokens, a list of tokens. These tokens, they have two main parts: the type of the token and the value of token. After that, the parser will check if this syntactically correct, and then it will generate a tree like that. So this tree will help us and help the automaton builder to generate our automaton. So let's jump to the code and we will build our lexer and then our parser. So now let's create a model called lexer. Inside that model we will create 3 different classes. The first one called class token type. It inherits from class enums. Then we create the different types. The first one is a tuple, is a pipe, and the second one is a literal. So let's import that enum class. From enum import enum. So let's create the second class. It's the class token. We will define the constructor. It accepts token type. Its type, it's a token type, and it accepts also the value. Its type is a string. So let's initialize that by doing type and self.value and value. So let's add one more function. It's just for debugging purposes. So we'll return a formatted string token. It has self.type and self.value. So let's create the last class. It's our lexer. It's our lexer. It will lex. Let's have a static method. It will lex the regex and it will return a list. So let's initialize an empty list of tokens and initialize our iterator while I lower than the length of the regex. We are ready to tokenize that. If regex in the position I equal a pipe, then we'll append to the tokens list. We'll append the token and we pass the token type pipe and its value. Otherwise it's a normal literal. Also token, and we'll pass the token type, it's a literal, and then its value. To regex, its value, it's regex in the position I. And let's increment our iterator. And finally, we return the list of tokens. So let's test that on an example of regex. Let's go to the main part and import the lexer class core.lexer import lexer. So let's print the list or let's do another way. Tokens equal lecture dot lex, and we pass it some sort of example of regex. Let's say, for example, A or B or C. Let's print out that. So let's run our program. As you see, the A is a literal, the pipe, it has type pipe, and the value is a pipe, and so on. Token B, pipe, and token C. So now let's create another file for the parsing model. So let's name it parser. Before jumping into the code and coding our parser, let's keep in mind that parser, they are a model that take an input and says if that input is respecting our rule of the grammar, and also it will build our AST abstract tree. So I prepared some sketching to present this concept of grammar. Let's see. As you see here, we have some letter English grammar. We have a phrase. A phrase, it consists of subject, verb, and adjective. And subject, it can be I, he, she, and so on. For verb, for just simplicity, I will use am, is, and are. And for adjective, also for simplicity, I will use just two words, happy and sad. Let's take the first example. I am happy. It's correct. Why? Because it respects our production rule. Let's go from here. Phrase, it's a subject. Oh, subject is a, so I have an A. Also, it's a verb, and the verb is am, and happy, also I have happy here. For this, it is correct in the real English grammar, but for simplicity I code this English grammar, so it is not correct because I don't have this defined in my grammar. So I will say this word is incorrect and it's not respecting the English rule and the production of this grammar. So let's move on. In our context, we are putting the regex grammar. It is simply an expression, and the expression, it will consist of two parts, term and sub-expression, and sub-expression to begin by a pipe and a term and expression, or it can be this expression, it can be an epsilon, an empty string. So for the part of term, it consists of two parts, factor and subterm, and this subterm, it will consist also about factor and subterm or epsilon, and this factor, it will be either an A, B until Z. So let's see this word. A or B or C, it's correct, because if we follow our production and start from this axiom expression, we will end with this word. If we do this word A or B, it's incorrect. If we follow this grammar, this regex grammar, we will end to nothing, so it's incorrect. So let's build our AST for the example A or B or C. So my cursor is on A, so I will load the axiom rule expression. It's our root. So from expression, I'm reading A, I will load the function term and the function sub-expression, because this rule, it says term and sub-expression, but for now sub-expression, it will be on the state of waiting until the term, it will return some value, and then sub-expression will continue running. So term, go for the rule term, and we will load the factor function and also the subtract function. So I'm reading A, so the factor, it is A or B or Z, so I'm reading A, it's correct, so it's an A. So here the function factor, it will return A. Subterm, it's either a factor or epsilon, and the cursor, my cursor is on a pipe, so simply this subterm, it will return an empty string. So my calling function term, it will simply return A, because A concatenated with empty string, it's an A. So this description sub-expression will run, and sub-expression it is a pipe term sub-expression, or it's a epsilon, but my cursor is reading a pipe, so I will load this rule. So I have a pipe and I will run the term function, also I will run the sub-expression function. So my cursor will increment by 1 and it sees a B. So the process will goes, term will load the factor, subterm. I am seeing B, so factor, it will return B. My cursor will increment by 1 and it says a pipe, and subterm, it don't know a pipe, so it will return an epsilon. It's an empty string. So the term will return a B, and the subcustom will run now, and we see a pipe, so it's a pipe, and I will load my whole row, term and sub-expression. From term I am seeing a C, so I will load factor, subterm, so the factor sees a C, factor will return C. So subterm, I am on the end of my regex string, so it will return an empty string. So this term will return a C, and the sub-expression will return an empty string. So from here this sub-expression will return a C, and this term it return B, and they have a pipe, so this sub-expression it return B or C. So the last function will return A, and I'm seeing a pipe, it will return A or B or C. So by this concept we will build our AST. So from now let's jump to the code and implement this concept. Let's go. As you know that we are building our AST tree, it's a tree, then it is composed with a different node. As we see in the sketching part, we have different nodes like pipe node, literal node, and some concatenation nodes. So let's build that before building our parser class. So let's do that by creating the first class called concat node, and let's define its constructor. It has a left child and right child. Let's initialize that by doing left and right. Let's add one more function. Returns a formatted node, concat node, and it has its left part and its right part. And let's define another class, another node. It's the pipe node, and it will contain the same as concat, and we will change only the formatted string with the pipe node. Let's add one more class called literal node, and let's define its constructor. It has only the value, and just initialize that by doing value equal value. Let's add one more function and return the formatted string literal node. We will display only its value. So we are ready now to go to define our parser class. So let's begin. Class called parser, which will has some attribute like tokens. Let's say it's an empty list. Also as the position of our cursor and the length of token. Let's say 0 and 0. Let's define our static method called parse, and it takes the list of token. So let's define the grammar, our regex grammar. It has exp, and exp will give term and subexp. Also subexp, which will has a pipe, and term and subexp, or the second rule is just epsilon. It can be epsilon or empty string. So let's do the term. It has factor and subterm, and subterm is just another factor and a subterm, or epsilon. Finally, we have the factor. It's just the alphabet A, B, so on to the Z. So for the first time, we will initialize our class attribute by the length of our tokens list, and then we will check if the length is less than or equal to 0, which means it is an empty list, and then we will raise some sort of exception by saying error empty tokens list. And we will initialize our tokens attribute by tokens, also our cursor by 0, and we will return whatever the axiom function will return, and we will name it exp. So for each non-terminal we will define a attribute. Let's say for now it is a static method, and we'll call it exp. Let's pass that for now, and we will create subexp, subexp, and we'll pass it for now. Also we will create term, which is also a static method, def term. We'll pass it for now. Also we will create subterm and factor. They are also a static method, def subterm, and we will pass that for now. And finally we have the method factor, and we pass it for now. Let's see our grammar. Our factor will define a, b until z. It is the more convenient one to define because it is simple. So we will check if our cursor, if it is pass the length of our token list, then we will raise a syntax error, and we say unexpected token. The token is parser.token at the position -1, and we will specify also the position. So the position is just parser pose. Let's continue, and we will check if the consumed token, it is a if not a literal, we'll take its type, and we'll check if it is not a literal, then we raise a syntax error because we are expecting only the literal type. So we'll do this. After that, we will consume our character and increment our cursor by 1. This just saying consume current token, and we will return our literal node with parser.tokens add position parser.pose -1. Why -1? Because we incremented, and we take only its value. So let's move on to the subterm function. We will check if our cursor pass the length of our tokens list, or the current token is a pipe, then we return an empty string. Let's check that by doing parser tokens parser pose, and we take its type, and we check if it is a pipe, then we return an empty string. Otherwise, we will run the two function, factor and subterm. Let's say subterm, we have factor. Let's correct that, factor and subterm. So we will run these two functions called factor and subterm. We'll do parser.factor and subterm parser.subterm, and we check if subterm returning an empty string, we will return the factor value. Otherwise, we will return the concatenation node of both result, factor and subterm. Let's move on to the term function. And in term function, we will run the factor and subterm function. Let's do that by doing factor will parse factor, and subterm we will run the method subterm, and we check if subterm return an empty string, then we will return the factor value. Otherwise, we will return the concatenation of the two value, factor and subterm. Let's move on now to the subexp. As you see, subexp is defined by a pipe. We should read pipe or an epsilon. So if we read a pipe, so we will load this rule pipe and we run German exception. Otherwise, we will return just epsilon. So let's move to the subexp. So in the subexp, we will check if we are at the end of our tokens list. If it's so we return an empty string. Otherwise, we will check if the token on this position it is a pipe. We'll take its type is a token type dot pipe. Then we will consume the pipe character by incrementing by 1, and then we will run the turn function, and we will run subexp function. And if subexp is an empty string, we will return turn. Otherwise we will return the pipe of the two value, turn and subexp. Okay. Otherwise, we will raise a syntax error. Let's copy that. Okay, syntax error as this. So now let's define our axiom function. It's our start point of our grammar. It runs turn and subexp function. So let's do that by turn and subexp parser subexp, and we check if subexp is an empty string. We will do just return term. Otherwise, we will return the pipe of the two, turn and subexp. So as you see, it's a hard concept, but when you understand this concept, and it will become easy to you. So reread the code and you will understand what we are doing and how we code this grammar to check if our tokens respect our grammar's lore, and how we will build the IST. So let's move on to the main part and do some testing to check. So let's import our parser from core parser. We'll import the parser class, and let's pass it this token list. Let's do parser.parse, and we will give them the list of tokens. Let's run this and see what we will get in this, and let's print this, or let's say it will return our AST, and we will print the AST. Let's run this, and as you see, we pass it a list of tokens of example A or B or C, and we get a pipe of literal A and piped with literal B and C. Let's check another example and do A concatenated with some K value, and we will see that we have a concat between A and K and pipe with the others. Let's run this and see. So as you see, we have a pipe of the concatenated node of A and the literal with piped with another pipe, and it's a literal B and literal C. So let's do something that let's try another example like that, A or K. It simply will return a concatenated node of literal A and K. So let's do something wrong that is not acceptable by our grammar. Let's say we write A or B. This is not correct, and we will return a syntactic error. As you see, it's a system error, unexpected token at the position 2, 0, 1, 2. So we are not expecting this pipe. But I don't know why it says system error. I think it is I write here system error. Let's print syntax error, not system error. We'll change it here and here on our code, also as here. So let's go back and rerun the test, and as you see, it's a syntactic error. It says the 2 is not acceptable, and I don't like this format token like that. I want the value, so I go to the parser and I will print value. Give me only its value. So let's go back to the main and rerun our test. As you see, it's a unexpected token or at the position 2. So for now, let's jump to the sketching part. As you see, remember this architecture. So for now, we build a lexer and we build a parser, and from now we will build our automaton builder. So as you see here, we have our Regex example, A or B or C. The lexer, it tokenizes and give us some tokens, and the parser will parse and give us this abstract syntax tree. As you see, it's A or B or C. In coding part, we will see something like that: pipe node of literal A, then a pipe, and literal B and C. So to construct our automaton from this abstract syntax tree, let's talk about some theory here. This is what we called a Thompson automaton. So for the building part and elementary element, let's say we have an A, we build something like that. We have a start point and end point, or start state or end state, and the transition with A. If we have a case A concatenated, we do something like that. From 0 we go to 1 with the transition A, and from 1 to 0 we go by the transition epsilon, and also from here to here we go with a B. Let's modify the number of states. Let's say it's 2 here and 3. Keep in mind that all what we will done here, we add the start point and the end point. So for the case A or B, we have the A, and also we have the B, and we merge that into the OR. We add the start point and the end state. We add transition epsilon here. For the A star, and this is out of our scope of this tutorial, we are focusing only on operation OR and concatenation. So let's introduce it. We have A block, and we do some looping here to make A star. So let's focus on this example. Pipe node with literal A and pipe node with letter A and C. So our abstract tree is something like that. A or another OR with A and C. This is our AC. So here we have three building parts. It's the letter A and the letter A also and the letter C. So we do automaton, Thompson automaton for A and for I and for C. So we have a pipe node for this two automaton, so we will build it. We have A and we have C and we do the automaton, the OR automaton. So we add also another pipe in top of this, so we have something like this. You remember we have from previous, we have A or C and we have letter A, so we add letter A and we do some piping between them. This is what we called a non-deterministic final automaton with transition epsilon transition, or in short it's an epsilon NFA. So for machine it's hard to traverse this automaton because we have a non-deterministic way, because if I am in the starting point I can't make the decision to go here or here because we have the same transition epsilon and they goes to the different state, so I can make a decision. So here we will convert this epsilon NFA to an NFA. So let's do this. Here we introduce another concept, we call it epsilon closure. So it means that I am from state 0. What are the states that I will go from here with epsilon? So from 0 I go to 1, so I put 1. From 0 I go to 3 with epsilon, so I put 3. And from 3 I go also to 4 by epsilon and 6 by epsilon, so I add 4 and 6 and so on. You can make it for 1, 2, 3, 4, 5. Let's say this example 5. The 5 we go from epsilon to 8 and 9, so I put 8 and 9. So keep in mind, any epsilon closure that has a final state like this and this, okay, let's do some back, and we have a 9 and we have a final state here and we have a final state here and we have a final state. So if all these states will be final, and we do this arrow like that. The second thing we will do is to remove every epsilon transition, all of them, and we will start building our automaton from this epsilon closure. So the idea here, I'm starting from 0. I say that 0, it has 1 and 3 and 4 and 6 epsilon. So I go for this state and they see that 1, it's go by 2 by the transition A. So I will make a transition from 0 to 2 by A. I go to the next one, 3. 3 it goes to nothing, so I'll skip it. 4 it goes to 5 by A, so I will do 0 to 5 by A, and so on. So 6 it goes to 7 by C, so from 0 I will go to 7 by C, and I'll keep doing. 1 it has only 1, 2 it has 2 and 9, 2 and 9, so from 2 I have nowhere to go and 9 I have nowhere to go. So let's see 3 it goes to 4 and 6, so 4 it goes to 5 by A, so from 3 I will go to 5 by A, and 6 it go to 7 by C, so from 3 I will go to 7 by C. So let's move on. For 4 it goes to 4. 5 I have 8 and 9, so 8 it goes to nothing and 9 goes to nothing. 6 also. 7, state 7 it goes to 8 and 9, and 8 and 9 they goes to nowhere. 8 also and 9 also. So let's add the final state. Here we have 5, it's a final state, so I will add an arrow like that, and for 7 I will add an arrow like that, for 8 also, and for 2 also, because 2 it has a 9. So here we should also convert this NFA to DFA, to a deterministic finite automaton. Why is this is not deterministic? Because we have from 0 we will go to 2 by A, and from 0 we will go to 5 by A, so it's ambiguous. We can't take the decision to go from here or here. So let's do that by introducing a simple concept to determinist this automaton. So we will do a simple table, and we have the transition A and B. So I'll start from 0. From 0 taking a transition A, I will go to 2. And from 0 with transition A, I will go to 5. So from 0 also by I made a mistake here. It's a C, not a B. Okay, so from 0 to 7 by C, so I will put 7. So I will take this new state to 5 and 5 and 7, I will add it here, so I will say 2 5 is a new state, and I will make the same process. From 2 by A I go to nowhere, and with 5 by A I go to nowhere, so I put there is no transition. So by 2 and taking C I go nowhere, and by 5 taking C I go nowhere. I'm finishing with this state. I still have this 7, I will add it here, and I will check for transition A and C. For 7 I have nowhere to go by A or C, so I put null. So keep in mind that every state that has 1 or plus final state, it will be a final state. So 2 5 is a final state, and 2 is a final state, so this state it's a final state. 7 it's a final state, so here it's a final state. So let's build now the automaton. We have the state 0 and state 2 5 and state 7. From 0 I will go to state 2 5 by A and to 7 by C, and this is a final state, and this is a final state, and this is an init state. So let's enhance this automaton by giving another names to this state. Let's see, 0 1 and 2. I'm renaming just the states. I'm sorry about this drawing, but so this automaton will represent by a deterministic way the regex A or C. So let's do it from let's see that a user gave us A, so I go from 0 down there, then I have a transition with A to the final state, so it's okay. Let's do a C, so I have another path for C, and I'm in the final state, so it's good. So now in our architecture and on the automaton builder, we will have a methods that give us all epsilon transition and can convert our automaton from epsilon NFA to from epsilon here, from epsilon NFA to NFA, and from NFA to a DFA. So let's jump to the code and build this concept. So now we will create our automaton builder model. So let's create a new file called automaton builder, and inside that file we'll create a class called automaton builder and create a static method called builder, and we'll accept our AST, and then it will return. Let's pass it for now. Let's call it build, and let's pass it for now. Let's jump to our Regex engine, and as you know, now we will change our generator function. So let's remove that, and let's copy that and return it in the function builder just to test that, and I will import that. I import the package automaton. So I will go to the Regex engine and I will change the code of our generation. Until now we've built our lexer, so let's do tokens, and we call lexer and do lex on the Regex. Then we call our parser to generate the AST, and we pass the tokens generator by the lexer, and it will return our AST. And then automaton will be generated by automaton builder build, and we pass AST, and we return finally this automaton. Let's import the package lexer also as parser. So from core dot parser import parser. Also let's import the automaton builder. So as you see here, we will not change anything. The generator is complete, and the acceptor is complete, and our match is complete. All our work will focus on the automaton builder. All the other things are proven that they give the right result. So we will build this and complete development of the build. This builder will return a deterministic finite state automaton. So let's jump right to the builder, and our builder will just return for now this automaton. Let's test that, and so we will remove that for now. Also we will remove that, and this automaton builder is just for A or B. Yes, it's just for A or B. Okay. A or B. So let's test that. If it is an A, it will return matching. If it is a B, it will return matching. If it is not, it will return not matching. So let's come back to our automaton builder. Here we will not, from now, we will not hard code like that. So we will make things more general, and they will return automaton based on our AST. So let's add some method attribute class called state. It will helps associating number to state. So inside the builder class, the builder method, we will initialize that state attribute whenever we call the build, and we will call another static method called build Thompson automaton, and we will pass it the AST, and then it will return a Thompson automaton. So it will return a Thompson automaton. So let's return this Thompson. Let's return this Thompson automaton. And let's define a new static method called build Thompson automaton. Inside it, we will check if, let's call that parameter a node, it's more convenient. If it is an instance of literal node, we will return the automaton builder, a new function. We will create it later. It's called construct literal node automaton, and we pass it that node. And other case also, else if is instance, the node is an instance of pipe node, we will return an automaton generated by construct pipe node automaton. I will pass it a node. Else if it is an instance, the node is an instance of concat node, we will return automaton builder dot construct concat node automaton. We pass it the node. Otherwise we will raise an exception, and we say unknown IST node, and we display this node. Let's add the other method. The first one called construct literal, and it accept node. Let's pass it for now. Also as another static method called construct pipe node, and it accepts a node as a parameter. Let's pass it for now. Also as another static method called construct concat node and is accepted node, and let's pass it for now. Let's import this pipe node. Okay, everything is good. So let's define each one of these methods. The constructs, we will build an automaton if it's the node it's a literal, and if it is the node is a pipe, we will build this on construction the automaton, and if the node is a concat node, we will build the concatenation. So let's start with the literal one. So we will declare an automaton, and the start state will be automaton builder dot state, and we will increment that by 1, and the end state, it will be automaton builder dot state, and we will increment that by 1 also. Automaton builder plus equal 1. Let's define our alphabet, the initial state and final state, and all state and authorization. Then we will return our automaton. Finally, we will return something like this. So for the automaton dot alphabet, it will be just the node dot value, its value. And for automaton initial state, it will be something like start. For automaton final states, you guessed it, it's end, and all state, it's the combination of initial and final state. Start, end, and for transition, we would say transition, it will be start node value and the end. So we've done with the literal node. So let's move on to the pipe node, and this we will create an automaton that accepts a regex with pipe. So before implementing this method, let's test that, and keep in mind that all these methods are recursion method. So I would, in like pipe node or concat node, I will also call the automaton build Thompson automaton on the right child or the left child. So it's some sort of recursion. So let's test the construct literal node automaton. Let's go jump to the main. Let's remove all this, and let's do tokens lex, and give it a regex like A. Let's import the lexer. Also ist will be the parser that parse the tokens. Let's import the parser from core.parser, import parser. So now I will test Thompson automaton will be generated by the class automaton builder, and we call the method build and we pass it the ist. So let's print each output like tokens, and for ist let's print the abstract syntax tree, and also finally let's print the Thompson automaton. Let's run this and see. So as you see, the list of tokens generated is one literal, and the ist is literal node, and for automaton it's alphabet is an A, initial state is 0, final state is 1, all states are the combination of the two, and transition from 0 to 1 I will take A. So let's pass to sketching to see that. As you see here, this is the case what we build now, 0 and 1, and the transition is by A. Let's go back to our code. So this is what we built for now. Let's return to the automaton builder and continue by creating the method that will generate the pipe. So let's do something like that. Automaton, it's also a new automaton, and Thompson automaton, but for the left it's automaton builder dot build Thompson automaton on the node dot left. Also for the right, automaton builder dot build Thompson automaton for the right node. So for the alphabet, it will be automaton dot alphabet is the combination of the alphabet of the automaton Thompson of left and right. So we will do something like Thompson automaton left union of Thompson automaton right dot alphabet, and here is also alphabet. For the automaton dot init state, it's a start. So for the start, it's our cursor state, okay, and we initialize our init state, and then we increment that automaton builder state by 1 because it is our tracker of the number of state. So then we'll build the end state, and we do something like automaton builder dot state, and we will also increment that by 1. And so for the automaton dot final state, it's the end. So for the automaton generated its states, it will be the Thompson automaton left dot states, and we do union with the Thompson automaton right, and we call its states. But also we would add the start and the end states to it. Automaton state union start and the end. For the automaton transition, this initializes by empty dictionary, and we will say automaton dot transitions dot update, and we'll do something like automaton left dot transition, and also we will update that automaton transition dot update Thompson right transition. And we will also add another transitions update, like for the start method we will go by epsilon to the first of each build automaton. So let's do that by doing Thompson automaton right initial state, and we pop its value. Also as the Thompson right of initial state, and we pop its value. Okay, and we will build the for the final states. So we'll do the Thompson automaton right, and we take its final state and we pop it to take its value, and we go from transition epsilon, and it will goes to the end. Also as for the Thompson automaton left, we take its final state and we pop its value, and we go by transition empty to the end. And here we are finishing this one. So for now we are building the pipe automaton. Let's jump to the main function and test this. So let's test A or B. Let's run this. Okay, it says okay, it is due to the circular. So let's fix that issue. It is due to the problem of circular import. So let's go to the automaton builder and we will remove this, and let's check the pipe node. Okay, here. So here I made a simple mistake. So automaton transition updates, but from star I will by epsilon I will go to the initial state of the right node and the left node. So let's do left. Okay, let's go to the main and we'll test this use case A or B. and we will see. So as you see, the tokens, the list of tokens is A as a literal, pipe, and B as a literal, and our AST is a pipe of literal A or B. So the alphabet is B or A, and we have the initial state is 4 and the final state is 5. All states are 0, 1, 2, 3, 4, 5, and the transitions are these. So you are wondering why the initial state is 4 and 5. It's due to the algorithm. I will go to the sketching and I will explain. So as you see here, our automaton builder, for the first time it will do a 0 and 1 for this state, and for the second time it will build the B literal, and we'll do 2 and 3, and then we'll add the start and the end by 4 and 5. And this is the algorithm. The number of states, the number chosen for states is not important. The important thing is transitions. So let's jump to the code and see that. 4 it will goes to 1 and 3 by epsilon. Let's see that. Okay, 4, where is it? 4, it's go to 0 and 2 by epsilon. So it's correct. And 1 it will go to the 2, 0 it will go to the 2 by A, and so on. So let's jump to the final touch for the concatenation node, and for building that it is easy. We do as previous, automaton, and we return an automaton at the end. So for the Thompson automaton left, I will call automaton builder dot build. Automaton builder build Thompson automaton for node dot left, and the same as the right. Okay, right, okay, and right child. So let's build the alphabet. Automaton dot alphabet eats the Thompson dot left alphabet union Thompson right alphabet union Thompson right dot alphabet. And for initial state, it is the initial state of the left node. Let's do something like Thompson left dot initial state. And for final states, automaton final state is the final state of the right child. And for all states, automaton dot states, it's the Thompson automaton left dot states union union Thompson automaton right dot states. And for transitions, automaton dot transitions, it's the Thompson automaton left dot final state will pop the value, and it will go by epsilon transition to the Thompson automaton write dot initial state and we pop its value. Okay, for okay, here we link the two automaton by the epsilon transition. We take the final state of the left automaton and we link it with the right with the initial state of the right automaton by the transition epsilon. And for the other transition, we'll do an update of Thompson automaton left dot transitions, and we do also automaton dot transition dot update, and we updated with the Thompson automaton right dot transitions, and finally we will return our automaton. Let's test that for the concatenation node, and let's do something like A concatenated with B. Okay, we have the same problem of circular. Okay, let's remove that. Let's jump to the main and let's run our test. As you see here, we have A and B, and we have concatenation of letter A and letter B. This means the IST, that means that A is concatenated with B. So for the automaton generated for this case, B and A as an alphabet, initial state is A, final state is 3, all state is 0, 1, 2, 3, and we have all the transitions. So let's jump to sketch and compare that. So as you see here, for the use case of concatenation, we have 0 and 1 and 2 and 3, and we have a transition by epsilon from state 1 to 2. Okay, 1 to 2 with, as you see, it's 1 to the state 2 with epsilon transition, and 0 the right automaton, 0 to 1 by A, and the left automaton is 2 to 3 state by B, and final state is 3, and the initial state is 0. So for now we've built all the necessary parts, but we have a simple issue. Here we are returning a Thompson automaton with epsilon transitions. The issue with that is it's not deterministic, which means we have with the same transition we can go to a different path and we can make our decision, and for that we need to convert that to a deterministic automaton. The type of that is an automaton. So our Regex engine, it accept only an automaton that is deterministic. So let's jump to our automaton builder, and here we will do simply, we call a method that's called toDFA, and for now we will build this DFA method in our class automaton. So let's go to the automaton. So first of all, let's start by defining our objective from this automaton class. This automaton class is simply a model of state machine. It helps in, first of all, defining an automaton. Then it checks if the automaton and epsilon NFA or an NFA or a DFA. And finally, we would have some method that can convert epsilon NFA to an NFA and finally to a DFA. So let's start by defining our first helpful function. It calls is epsilon NFA. It checks whether the existing automaton, the given automaton, is it an epsilon automaton or not. So we'll do that by checking all transitions and then check if the symbol of the current transition is a epsilon or an empty string. Then we return it true, otherwise we return false. So we will define a function that will help to check if the current automaton is an NFA. So we will check if that automaton is an epsilon NFA or the length of its initial state greater than 1. Then we say it's an NFA. Also, we loop over all transitions, and if we have the transition that goes to a multiple states, which means that if the length of the destination state they pass a 1 in length, then we return true. It's like I give this example, like let's do a comment, like 0 state goes with the symbol A to multiple transitions, multiple states like 1 and 2. Otherwise we will return false. Also, we would define a function that check if the current automaton is a DFA. So we simply return the not of self is NFA. So now our purpose of this automaton class is to converting the automaton from epsilon NFA to NFA and finally to a DFA. So the first one is epsilon NFA to a DFA. We will pass it for now, and for the other one is to from, or we'll say to a DFA. So let's pass it for now. So let's define our epsilon NFA to an NFA. So for the first time, I will check if the current automaton is a epsilon NFA. I will do some functionality here. If it is not, otherwise we will return the current automaton. So let's begin defining what we would have in this test. So first of all, we would initialize, or we should have all the epsilon closure of all states. So let's have a simple set all states, and for the new transitions also. And from here, for each state, we need to know all states with epsilon star transitions. For that, let's do some for each state in states. We would have the all epsilon closure for the state S, and we should have some helpful function that will return its epsilon closure. Let's name it epsilon closure of state, and we pass it the current state. So let's define this function, and it accepts a state. So first of all, we will need to ensure that we are not checking and rechecking some states already seen. So that will track all states, that already seen. So to avoid the circular search of epsilon closure. So let's begin by we check if the current state, the past parameter state, is not in the definition of our automaton. Then we raise an exception that says state not defined. Otherwise, we will return self dot, and we will define this function get epsilon closure of state, and we pass it the state and states already seen. So let's define this function. Define function, it accepts state and states already seen. So we will check also if the past state not in self states, will raise an exception that says state not defined. Otherwise, we will go recursionally and call a recursion function, go recursion epsilon closure of so from this current state we will check other states that are linked with it with epsilon transitions. So we give it our tracker of states already seen, and let's define this function def and accept states and states already seen. And so from here we will go recursionally and check for all states that can be reached from the parameter state with epsilon transitions. So we have a variable called states with the empty set, and this all states variable will add the states, and also for the states already seen we will append its value to it. And we will check if the state, if this transitions is not null, which means that this transition it exists in our transition definition of our automaton. So then we will loop over all transitions in self.transitions, and we take all transition with epsilon symbol, and this it will return every state by the transition s. So for example, we would have something like if we have 0 and transition epsilon, and we have 1 and 2, this it will return a set of 1 and 2 because we take an epsilon transition to state 1 and 2. So if the current state is in states already seen, so we continue. Otherwise, our container of states will update it with self get epsilon closure of states. We go deeply in our automaton in a recursion way, so we give it states already seen. Okay, and finally we will return all states. So for now I am sure that this epsilon closure will return the set of all transition by epsilon associated with this s. So now we continue our algorithm to convert our epsilon NFA to DFA. So now we should eliminate all epsilon transitions. So I should define a method that eliminates epsilon transition. So let's define that. Def eliminates that. Okay. So it's a simple method that deletes all transition with epsilon. So we should get all the transition that is with epsilon transition. For doing that, we should filter our list of our transition. So by giving to the filter function a lambda symbol and the symbol at position 1, it should be epsilon, and I will pass as a parameter the self.transitions. For now, I will loop over each state in the state to delete, and we will simply do del self.transition. So let's come back. So now we are eliminating all epsilon transitions. Next, we will, after that, after we have the epsilon closure, for each state of our automata. Now we do changes on old automaton A to new automaton prim. And by changing transitions and final state set if possible. Remember, in the section of sketching part, in the converting of an epsilon to a DFA, we are searching for all epsilon transition, all epsilon closure transition, then we eliminate all possible epsilon transition, and then we will change our automaton. In the final state, we will check if the epsilon closure contains a state that is final on the old automaton, so the current state will be final. So let's do that. We will loop over all states in the epsilon closure state, and then for each state in epsilon closure state, we check if state is in self.final state of the old automaton. We'll simply do self.final states. We add this state. So in that, we are guaranteed that this state it's final on the new automaton. So the question what we need to answer from now, it's what are the transitions of state. What are these transitions? So after founding that, we simply add it to the transitions of state, which means state and symbol and state. So our result transitions result, it's defined by a function called set transitions for state, and we pass it the state and the state. This is the current state, and this is the state from the epsilon closure of this state. So let's define this function. Let's come back here and do def to accept target state and dependency state. So first of all, we need to get all transition of the dependency. For that, we will using the filter function, and we declare the variable called dependency state transitions. It's a list of filter. We pass it lambda function and state, the parameter state symbol, and we take the first parameter and if it is equal to dependency state, and we pass the self transitions. So now I have all dependency state transitions. So let's initialize another variable called other possible transitions, and we let it for now empty. Here we will initialize with transitions for target state, and for each state symbol in. Okay, I should define another variable also called transitions copy itself of transitions copy. So making copy to avoid changing the original transition for the given automaton. So let's initialize the transitions for the target state. And transitions copy, and if state is equal to target state, we then check if state symbol in other possible transitions. So we update these other possible transitions to be for the state symbol, and update that to be state symbol, and do transition copy for the state and symbol. Otherwise, other possible transition will be state symbol, and for transitions copy state symbol. So now we will add in new transitions for target state. To do so, we need to loop on every stage in dependency, every transition in dependency state transitions, and if target state symbol in other possible transitions, then we make an update on our other possible transitions with target state and symbol, and we update that by transitions state and symbol, and we do a copy of that. Otherwise, we do other possible transitions for target state symbol and give it self dot transitions and state symbol, and we do a copy of it. Finally, we will return other possible transitions. So let's go back to our method epsilon NFA to DFA. So in our result transitions, we have all the new transitions of the state. So for every result transition in results transitions, if result transition in new transitions, if it is in the new transitions, then we'll simply add it by doing rt update result transitions of rt. Otherwise is not defined in the new transition, so we do transitions directly update result transitions. So now if length of the new transitions is bigger than 0, so we have a new transitions for the new automaton, so we do self dot transitions clear, we clear the old one, and then we update by the new transitions. Finally, we will return self. So for now, we are defining the epsilon NFA that turn the epsilon NFA to a DFA. So let's jump to the code, to the main part, and check if everything is good. So before giving an example about what we built until now, so let's come back to our automaton class, and let's make this correct, because in the NFA we will not check the length of transition but for the initial states. If we have a multiple initial state, then it is an NFA. So let's come back to the main part and let's delete that and do some tests. One example, let's import that, call that automaton, import automaton, and the test that we will build now, let's go to the sketching part and see. As you see, this is the test that we will build, and after making conversion we will have something like that. So it's basically an automaton for A concatenated with B. So let's come back to the code and initialize our automaton. Say automaton with alphabet A and B. For the initial state is 0, for the final state is 3, for all state is 0, 1, 2 and 3, and for all transitions we have from 0 taking a symbol A will end on the state 1, and from 1 taking epsilon transitions will end on the state 2, and from 2 taking B will end on the final state 3. So let's print before conversion. Let's print out that automaton. Let's check if it is an epsilon NFA. So let's do automaton that is epsilon NFA. That will print it's NFA. Otherwise, let's print it's not NFA. Let's do the conversion. New automaton. So we'll do automaton dot epsilon NFA to A NFA. So let's correct the name of this function. It's not from epsilon NFA to the FA, it's epsilon NFA to NFA. So let's come back to our automaton and let's correct that from epsilon NFA to NFA. So let's back to the main part and we will print after conversion. We will have the new automaton, and let's check if it is an automaton NFA or not. Is NFA. Print it's NFA. Otherwise, print it's not NFA. It's a TFA. It's a little mystical. So let's run this. As you see, this is our automaton definition, and it's an let's change this. It's an epsilon. It's not an epsilon. So let's rerun. So as you see, we have a transition with epsilon, so it's print it's an epsilon FA. So after the conversion to a non-deterministic, so this is the conversion. So from 1 taking B, we are in the 3. So let's check that. So as you see, from 1 to 3, we are taking B. So let's back to the code. So that is correct. And also it is not a non-deterministic because we don't have from like example, we don't have a transition with the same symbol to other. We don't have a multiple transition with the same symbol from one state to others. So every one it has one transition. So it is a deterministic. So we can make a decision. So let's take E, and I will make a decision to take this path, and in the final state. So let's back to the code. So as you see, it prints here. It's not an NFA. It's not a non-deterministic, but it is a deterministic. So that's good. What we build now, it's true, and they give the right result. So let's come back to the automaton and build our main function that automaton builder will use. The automaton builder, it's just waiting for the implementation to convert in an epsilon to a deterministic one. So let's come back to the automaton and let's build this function. So first of all, let's check if the current automaton is an epsilon FA. If it is the case, we simply run the conversion of epsilon FA to an NFA before starting to make the conversion to a DFA, to a deterministic one. So if it is a NFA, then we do our processing. If it is not, we simply return self. So the algorithm to determine our automaton is really simple. Just we need some variable to the new automaton. So let's make new transitions. It's an empty one. This is the transition for the automaton after determinization. So also new states, let's set it for now to a empty set, which basically represent the new states for the new automaton. Also we need new final state, so it's basically an empty set to represent the new final states for the new automaton. And also we need a helper variable that's hold states already processed, and let's set to an empty list. So it track the states that already processed. Also we need to initial the states that need processing. For these two variables, there are two stacks. The first one, it track the states that already process, and also this one, it's a stack that track the states that need processing. So let's initialize it with the initial state of our current automaton, and let's do another variable called name mapper, because at the end we would have some states that have a list of number, like this one, for example, state like that, its name like that, 1 2 array, and we take in some symbol, for example. Oops. Second, let's minimize that, and take in some symbol and go into some state like this, like this. So we need to give this state another number just to simplify the automaton. So let's say we're naming to 0 and going with A. We will go to 6. It's just an example. So you get the idea of doing that. So the name mapper, as I told you, it helped to give new name to state after determination. And also we would have a state number initializes by 0. It will track number of states that we have. So the algorithm is too simple. So we loop until the stack of the states needs processing is empty. And if we process some state, we put it in the stack of state already processed to keep track. So let's do it. So while the length of states need processing is greater than 0, then the state variable will hold states needs processing, and we pop the value in the stack. So if this state that I'm in states already processed, so we continue. If it is not the case, I need the destination states. So self.get transitions of states. So let's implement this one. It will return all the states that are linked with the state by all symbols in our alphabet. So let's define that function. So def so basically what we are doing now, so it is too simple. We'll check if state is none, raise an exception, error, none value. If len dot state is less than or equal 0, we return an empty dictionary. So we will initialize our return values with an empty text dictionary. So for each symbol in self alphabet, initialize a variable called founded state with an empty state. So for each state in and we sort that state list, and then we check if self dot transitions and s with the symbol is not none, then we update our founded state to be self.transitions s and symbol. So after that, the state transitions will hold a tuple of sorted state, then the symbol, and we will return a tuple of sorted founded state if in case the length of founded state greater than 0, otherwise we will return an empty tuple. So now we will return the state transitions. So as I said, this function will return all the states that are linked to the state passed by all symbol transitions. So now we will continue. For each element in result, let's rename it with the result. Nope. Let's eliminate that line. So we check if len of result state is greater than 0, then for the stack of state already processed we append that state. So, and we check for each state in result states if the first element not in name mapper, then for new states we'll add the state number, and then we update our name mapper for this tuple to be the state number. So after that we will do a checks for new final states, and for that we do for each sub state in this tuple, if substate in self dot final state then the new final state will be added to the new final state variable with the state number. After that we increment our cursor state number plus 1. Then we will check if result states for s is none, or the length of result state of s is less or equal than 0, then we continue. And if result state of the state is not in state already processed, we will add it to the need processing. State need processing, append result state of s. So here we are sure that the state has transitions to other ones. So new transitions, update s is result. So now we are at the end. So for initial state will be initialized with name mapper for self.init init state, and we pop the value, and it is a tuple. So for the final state will be new final states, and self.states will be new states. Okay, and also self.transitions we will initialize it by an empty dictionary. And finally, what we will do, we simply map each new state with its corresponding number. After that, it's just to simplify things, it's the same automaton if it recognize the same language as previous. So let's do that for each state and symbol in new transition. We will do self.transitions for name mapper of state and symbol. We will return the new one, name mapper for new transitions of state and symbol. And at the end we will return self, the current or the new automaton converted. So let's jump to the main and test this function that do a conversion to a deterministic automata. So let's move to the sketching part to see what are the examples that we will be testing now. As you see, the example that I will test is the regex A or C. So finally we will go for all this process converted to DFA, and finally our DFA should print this automaton. If it is the case, so all is good. So let's hard code this automaton to see the results. Let's jump to the code. So I have prepared the automaton. I just do a paste. This is the automaton. The alphabet is A or C, the initial state is 0, the final state is 9, all states are from 0 to 9, and this is all the transitions. So let's call and print the final automaton. Deterministic. So let's do result. It's automaton, and we will call the conversion to a deterministic automaton. So let's run that and see the result. As you see, this is our result. We have the initial state is 0, the final states are 1 to 2, and the states are from 0, 1, 2, and the transition are from 0 to C by 2 and from 0 to 1 by 1. So let's check that. So we have 1 and 2 as a final state. So as you see here, we have 1, 1, and 2 as a final state. So we are okay. We have 0 and 1 and 2 as all states. So let's see that. Okay, we have in initial state 0. Okay, this is 0 as the initial state, and we have transition from 0 taking C to 2, 0 taking C to 2, and 0 taking A to 1. 0 taking A to 1. So all is good for now. So we are at the final of our project. So our engine Regex, it is terminated. Our automaton builder is terminated. Our automaton also, our lexer, and our parser. So we are proven that the automaton builder will build the right automaton as a deterministic one. So let's test our whole package. Let's remove all that, and we'll do some simple example. Import that from core Regex engine, import Regex, and we will test that if Regex match will give the Regex, regex. I will take as an example A or B or C, and we'll give an example. Let's say A. If it is matching, we'll print matching. Otherwise, we'll print not matching. So let's run this and see. As you see, it's a matching. If we test B, it's matching. If we test C, it's matching. And if we test A concatenated with B is not matching, because it is either a B or a C or a A. So it says not matching. Let's change this to be a concatenation of A and Z or C. Let's say it's A concatenated B or C. So this, it will be matching normally, and if we do C, it is matching. If we do A and B and C, it's not matching. So our engine is complete. So now we've completed our Regex engine that supports the operation OR and concatenation. So have fun to copy this code and add more operations like features, like plus operator, which means one or more, and escaping character, also as clean star, and finally the grouping. So guys, have fun and thank you for watching, and see you in the next lab for new challenge.